Hello to everyone out there. Welcome to Calculus 1 with 3. And today is our first lesson. We're going to start talking about functions, and they are one of the most fundamental things we have to use in calculus, so it's a good place to start. So our first task is to figure out what exactly a function is. And informally, a function is just a rule or a machine that takes some input and produces exactly one output. You may have experience with functions such as, say, y equals 3x plus 4. And this clearly takes one number, x, applies this rule, called the function, 3 times x plus 4, to produce another number y. For example, if we were to put in the number 1, we would get 3 times 1 plus 4, which is 7. And you can think of this as a machine that, just a little black box here with some gears in it, and take this x, we plug it in here, and it pops out this y value, and that follows the rule that y equals 3x plus 4. And that's just a general intuitive idea of what a function does. If we want to get more formal about it, a function is simply a map which takes things from one set, and you think of a set as a collection of objects, from one set to another set. And we write this f, if that's our function, colon x arrow y. And that means it's taking elements from this set, x, and turning them into elements in this set, y, based on this rule f, which we call a function. And to get an example of what this might look like, let's draw a couple sets here. Let this be set x, put some numbers in here, say how about 7, 3, 4, 6, and 2. And we'll draw another set over here, y. And we'll put more numbers in that one. Let's say 1, 0, 2, 10, 5, maybe 3, 7, and 9. And these are just our sets. And we're going to make a function from f from x to y. And we'll write that just as before, f from x into y. And how are we going to define this function? Let's say it takes 3 to 0, and it takes 6 to 0. And we'll just indicate this with arrows. Maybe it takes 2 to 7, and maybe it takes 4 to 2. So here we've just defined a function. And we know it's a function because every element of the set x gets mapped exactly to one element of set y. If, for example, 3 got sent to 0 and 1, this would not be a function. And we can use this diagram to consider two important principles or components of a function. These are the domain and the range. The domain is defined as all elements of the set x for which the function sends x to a member of y. For example, here 3, 6, 4, and 2 are in the domain because they're defined by f. They send this element in x to some element in y. Because the function doesn't send 7 to anything, it's not in the domain. The range is the set of all elements in the set y which get hit by elements from x that get mapped into y. For example, here's 0, 2, and 7. And these are the only elements in the range. And what's interesting is that the domain is larger than the range. And this is always true. It is always at least greater than or equal to the range, because if it were less than the range, then the range would have some element which was hit, two elements which were hit by the same element in the domain. For example, if 3 got sent to 1 and 0, the domain of the function could be smaller than the range. And that's not allowed. So, in calculus, we typically consider functions that send a real number, denoted by this fancy r, to another real number. For example, let's take this function y equals x squared. Written like this means we take any real number, x, plug it into this function, and we get x squared, which is another real number. So let's ask ourselves, what is the domain of this function? Well, what numbers are we allowed to square? We can square anything. That's a defined function. Every number in the reals will when it gets squared, will end up in the reals. So that means the domain is everything. that is negative infinity to infinity. How about the range? When we square a number, we never get any negative numbers from a square. So we could get 0 if x was 0, but we can only get positive numbers if x is not 0. Therefore, the range of the function is just from 0 to positive infinity. And this square bracket indicates that 0 is in the range. Now, domains can change if we change the sets on which a function is defined. Let's take, for example, now the function given by y equals the square root of x. In this case, the domain is not all real numbers because we don't have, when we have, say we were to put negative 1 in here, the square root of negative 1 is not a real number, it's imaginary. Therefore, the only ones that will produce real numbers are those for which x is positive or 0. Therefore, this time the domain is from 0 to positive infinity. Now, what if we were to change the sets on which this function were defined? Suppose we change the function from going to R, we change it going from the reals to the complex numbers. This includes numbers that have imaginary components like I. Now, every element of x gets sent to something in the complex numbers, because say we took negative 1, the square root would be I, and that is in the complex numbers. Now, that means the domain of the function is again negative infinity to infinity, because everything in this function is defined. We can even concoct more strange domains if we're a little creative about the functions we use. Say we make a function from R to R again, and we're going to define this function y equals 1 over round x minus x, where round x simply rounds whatever you put in to the nearest integer. And it's clear that if we put an integer into this function, we'll get itself minus itself, and we'll get a 1 over 0, which isn't allowed. Therefore, the domain of this function is the real numbers except for the integers, which is kind of strange. And so, now that we've explored some of the abstract properties of functions, how can they be used for calculus? Well, calculus is fundamentally about problems of change and amount. And we write functions to relate quantities so that we can study their change and how much of a certain quantity exists. Say, for example, we wanted to compute the volume of a box. Something that looks like this. And say it has some height, h, some width, w, and some length, l. From geometry, you know the formula for this volume, V equals h times w times l. Now, this is a function that takes three variables, three real numbers, h, w, and l. In fact, it takes three positive numbers, h, w, and l, because we don't consider negative numbers to have any real meaning of length. Now, suppose we wanted to study how much bigger the box got if we changed the height. We can think of this graphically by adding some h here. Like this. Call this h a delta h for a change in h. This delta sign just represents a change. And so how could we compute this change in the total volume? From before, we know that V, the volume, equals h, w, l. So our new volume, V new, we'll call this, is the new h, which is h plus delta h, wl. And now we've inputted a different value for this variable here. Instead of inputting h for our function, we put in h plus delta h. And we can compute the difference of these to find the change in volume simply by subtracting this equation from this equation, and we get delta h wl. So this tells us if we change h by a certain amount, the volume will change proportionally by delta h times wl. And eventually we'll be able to apply calculus techniques to determine how quickly this change occurs, whether it depends on the current size of the box, for example, and all sort of other interesting stuff. For example, maybe how big the box can be if we have a limited amount of material. And so this is some kind of motivation for why we would use functions in calculus. And soon we'll be exploring some more properties of functions and how they can be applied to calculus techniques. But until then, take it easy.